Hi, welcome. So, this is the very first in hopefully a long series of videos brought to you by the Penn Yan Public Library. So, we're calling this Ask a Scientist because what we really want you to do is ask your own questions. I've spent 12 years teaching college students and asking and answering all sorts of questions. So, what's a GMO? Is gluten really good or bad? Do these salt lamps really do anything other than look cool? Lots of different questions. Climate change, anything you really want. But in order to get things started, I came up with my own. So we'll start with my own question that I came up with, which I think is interesting. My expertise is chemistry, but I'm willing to talk about just about anything. Food, environment, chemistry, biology. I'm not a genius. I don't know everything, but I know how to look up things in the scientific literature and do my best to explain things in ways that hopefully anybody can understand. And if you can't, ask more questions. I'm always willing to follow up and help. And if I can't answer it and I don't have a good answer, then I probably just won't answer it. But again, this is hopefully a great series from the Penn Yan Public Library, but even if you're not from the area, feel free to ask and contribute. This is for everybody to check out. If you haven't been to the Penn Yan Library, it's a great place. When it opens back up, everybody should go and spend more time there. In the meantime, they've got great programming, hopefully like this one. So, my first thing I wanted to talk about is the pressing question that everybody's always thought about, and by answering this, we'll save the world. No, not really. My question is, why are all my plastic containers orange? So, I like to save these. Come from Chinese restaurants, takeout, soup from Millie's Pantry, all sorts of places. Why do they change color? They used to be a nice clear plastic, and then now they're orange. And I'd like to explain how that works. So you may have noticed, right? So you may have figured out the first piece of this is if you have anything tomato-based in your Tupperware, in your plasticware, like tomato soup, SpaghettiOs, ravioli, I got kids, they eat a ton of this kind of stuff, you store it. Eventually, your plastic stuff ends up turning orange. So tomato is generally the culprit, you're actually right. But why, right? What is it about tomato that ends up staining this plastic? Because you can't get it out. You can scrub it all day, put it in the dishwasher, lots of heat, lots of soap. It's still orange, right? The more you reuse it, the more orange you get. So why? Well, what's going on here? What is magical about the tomato that is causing this problem and giving that red stain to it? And the answer lies in chemistry in this case. So tomato's not the only thing that can do this, but it's the most common one in our diets. And what happens is the red in tomato is quite literally finding its way into the plastic container, right? So it's not bright red because there's only a little bit in there. If you somehow manage to contaminate it a lot, it'll get darker and darker and darker, and eventually could potentially look red. I'm not sure that's ever happened. But the culprit in this case is a molecule called lycopene. Lycopene is present in tomatoes. It's present in fruit and vegetables that are red. It's not the only thing that causes things to be red, though. So watermelon is red, tomatoes are red. Have you ever seen a red carrot? The red comes from a molecule called lycopene. But strawberries, cherries, raspberries, things like that, they don't contain lycopene. So they shouldn't have the same sort of effect. So you've got some mashed up, some macerated strawberries hanging out in your containers. It should not stain them the same way. And there are more than one thing that's red. So natural food dye, a lot of times they'll use that lycopene tomato-based molecule just individually itself, not necessarily tomato paste or something. But that's the culprit. So that's just a name, right? So okay, he says lycopene. It sounds sort of scientific, but I can do a little better than that. I can explain it a little bit better. And so when you have plastic, right, and we kind of need to know a little bit about, what is this made of, right? So you can even see maybe this is even a little bit orange. All my stuff is a little bit orange. I don't segregate my plastic into tomato containing and non-tomato containing. So our periodic table, this is the table that basically is an organized list of every type of atom we have in the known universe. And if we look up in the top right of that, there's atoms you might be familiar with, like carbon, hydrogen, oxygen. We use those, and those are what make up plastics. The same sort of molecules, carbon and hydrogen, that make up lycopene. So there's a little bit of similarity there. So the problem with chemistry is you can't really tell, you can't see atoms. We just see these structures, this substance that we're used to, this clear-ish plastic. If you could zoom in on that on the atomic level, it would look a little bit like this, right? So this is like microwave science. I'm using ramen to illustrate my point. But the neat thing about this brick of dried ramen is it really actually approximates what this plastic would look like if you had, Superman's microscopic vision and could zoom in and see it. So everything's kind of folded in on itself, right? So it waves up and down. It's all packed kind of tight, right? So if instead of ramen noodles that are dried, these are a bunch of carbon atoms strung together to form this very same sort of shape. That's really a pretty good approximation of what this plastic looks like, right? So this and this, they're very similar as far as that goes. So lycopene itself is a long molecule made of the same kind of stuff. So what's happening when your lycopene is staining the plastic is it's quite literally finding its way into this plastic system. So back to the kitchen. I'm going to imagine this twist tie is my lycopene molecule. And it's actually not that far off because although, of course, there's much more to it, and protons and neutrons and electrons, it's this long, straight molecule. So quite literally what's happening with your plastic is it's incorporating itself into the plastic, right? And so just like if I were to make this in the microwave with some water, heat it up, this would soften and become a little more flexible. The plastic does when it warms back up, when it warms up as well. So if you heat tomato soup in the microwave, or soup that contains a little bit of tomato flavoring, lycopene, things like that, this will soften up, right? I'm not going to do that. And then incorporate and sort of wrap this lycopene molecule, which I'm using my twist tie to represent, and it actually kind of gets stuck in there, right? Of course, if you let ramen dry out, it'll get hard again. If the plastic cools back down, it'll get hard again. So everything will get kind of stuck in there and incorporating that as far as that goes. So that's part of why it stains. Another thing that we can use to sort of understand this is you've probably heard the term, and again, kitchen, common sense or sort of, kitchen knowledge comes in handy over and over again in chemistry. Is you've heard oil and water don't mix, right? So tomatoes stain plastic, strawberries don't really, right? For most of the time, that's how it's going to work. The principle of sort of oil and water don't mix applies here. So oil and water don't mix, oil and fats do, right? So you can mix olive oil and butter, melt them together in a pan, and they'll combine perfectly, right? So you have this a mixture of oil and butter, because on the molecular level, right? And if we could see these things, they're very similar. So these are two similar substances that kind of work together, butter and vegetable oil, right? So they're both fats, right? We can kind of make some sense out of this, but that works even on sort of this tiny atomic level to help things make sense. So they're similar structures, right? So the lycopene and the plastic have a lot of similarities. The biggest difference really is a little bit of what they're made out of, different atoms, but also that plastic really is massive, right? So this huge piece of tons and tons and millions and billions of atoms all connected together. You got a plastic, but it still has some flexibility and can incorporate a molecule that's kind of close to it, right? So they're like two oils in this case. In the chemistry terminology, we call those hydrocarbons, right? So things like gasoline and wax, they behave more like oils and they tend to mix well. So they're similar structures as far as that goes. So hopefully that helps you understand things a little bit better. There's a lot of cool science that goes on in the kitchen, but of course you're welcome to ask just about anything. Maybe I'll be able to explain it with ramen again. I hope so. That was kind of fun. So I'm going to leave you with two jobs, though. So please ask a question, right? So what are you dying to know? I'm happy to attempt to explain it, and if it's controversial or unclear, then we can talk about that too, and science and sort of how we know things. But again, this is hopefully going to be a great program put on by the Penn Public Library. So ask lots of questions. If you see this posted on the library page, ask there. If you see this, or if you're watching it directly on YouTube, ask in the comments down there somewhere. I'm happy to look. And then I'll leave you with a question as well. So, lid, bowl, right? All of my lids are more orange than my bowls, right? So why do you think that might be? So that's my question for you. Feel free to answer in the comments or wherever is convenient to you. Maybe you'll even win a prize. I don't know. This is my first time doing this. I'm just guessing. But yeah, hopefully you enjoyed. Again, please ask lots of questions. This is Ask a Scientist with Dr. Robak and the Penn Public Library. Have a good day.